All right. So basically, you recall a little bit about the central limit theorem. Is somehow is some result that relates to this random variable. This is a random variable, right? Okay. Your random variable is basically normalized, all right? And it says something about the distribution of this random variable. It says that this distribution will be approximately normal 0, 1 when n tends to infinity, right? So this is what you learn, okay? In maybe second year, and then the way they prove it is to use moment-generating function, right? The proof is actually quite long-winded, okay? Using moment-generating function. So now that you have studied something about convergence, right? You perhaps can see that what sort of convergence is this? There are three modes of convergence. Which mode of convergence is this? Is it a result about convergence in probability, convergence in distribution? Which one is it? Convergence in probability or convergence in distribution?
Convergence in distribution.
Okay, clearly, right? Because the result is saying that when the sample size is large, the distribution of this random variable is going towards n01, right? So this is a convergence in distribution result, yeah? So if you're going to write it in the notation that you just learned, you would write something like this. You would write it as Sn over n subtract mu over sigma of this converges in distribution to n01. Okay, so this is essentially so your central limit theorem is essentially a kind of result about convergence in distribution, right? It is saying that if you have this random variable, right, as your sample size gets larger and larger, its behavior, right, the distribution of this random variable will get closer and closer to standard normal, right? Which means basically for n large, right, you can use the normal theory to do things like, for example, calculate probabilities, calculate confidence intervals, okay, for mu. So this is the use. And okay, so this form is actually easy to remember now, right? You know that this part here is the sample mean, right? So this is a subtraction of the expectation of the sample mean, and here this part is the standard deviation, right, of this Sn over n, right? Okay. So remember, okay, I should say this is called the SE, right? The SE of Sn over n. Okay. Now, so now we want to look at more detail, right, about the conditions about this x1, all these things, your x1, x2, and so on, right? What are the conditions? Okay. Okay. The first one, of course, we already know that they have to be IID, right? Okay. Independent and identically distributed, right? Okay. What further assumptions do we have to make? do you have to specify the distribution of x? Do you need to know it? Do you need to know whether x is exponential, chi-square, whatever? Is it dependent on the distribution of x? Anybody? Ice Raya, you say yes. It depends on the distribution. So you are saying that some distributions this result will work, and some distributions it won't work. So how do we decide in that case which distribution? Then Xinjie says no, it does not depend on the exact distribution of x. Okay, so then what does it depend on? The sampling distribution of the mean okay. The sampling distribution of the mean for a random variable will approximate a normal distribution regardless of that variable's distribution. Okay, this is the reason why your central limit theorem is useful, right? Because it basically is a result that concerns the distribution of the sample mean. Okay, it turns out that the sample mean, right, regardless of what your distribution is, the sample mean that you find, right, its distribution will approximately be standard normal when the sample size is large, regardless of the distribution. So this makes sense because your sample mean, right, it should estimate the population mean properly, right? As you have seen the theoretical results like convergence in probability, right? So we can establish that the sample mean converges in probability to the population mean. So in this case, this is a result about the convergence in distribution, right, of the normalized sample mean to the standard normal distribution, right? So it should not depend on what is your x, right? Otherwise, this theorem will be almost useless to use because there will be too many situations, right? You have to consider. So we don't need to know, no need to know, but you need to know. You need to assume two things. You merely need to assume that expectation of x equals to mean is finite, and the variance of x. So I will say distribution x1. I just put x1. Okay, is also finite. Okay, you only need to make these two. As long as you have the random variable has a finite mean and finite variance, this result will work. Okay, so you will get your central limit theorem. Okay, so these are the only conditions that you need. All right. So in fact, so today what we're going to learn here is that in fact the CLT is guaranteed, right? We want to check conditions that guarantees the CLT. CLT is guaranteed if either one of these two conditions are satisfied. So we won't go through the proof. The proof is actually quite complicated. But we only look at the conditions. One is called the Lindeberg condition. The other is called the Lyapunov condition. Okay, so the Lindeberg condition and the Lyapunov condition. So then, so today we will try to see how to check these two conditions. Yeah, you can. So therefore, you can claim that CLT. You can invoke CLT by checking these two conditions. Okay. So what are these two conditions? So I'm just going to start on the Lindeberg condition now. So the Lindeberg condition. So you have the following. Okay, so the Lindeberg condition basically is about this limit. Yeah, the limit that this term here is equal to 0. The limit of this expectation of this is the second moment. Yeah. So your y1 is defined as the centered random variable. Okay, where your mu is the expectation of x1 and sigma square is the variance. Okay. So that's where you need the assumption to come in, right? Okay, so your y1 is actually this is the centered x, okay, variable. Okay, this is the second moment, right? This part here is the indicator function, right? Indicator function for this condition. So basically this this thing here will only be y1 square if this condition is true. Yeah, the absolute of y1 is more than this amount. Okay, so this is an indicator function, right? This is what we call a truncated moment, right? Because instead of evaluating the whole moment, right, you are evaluating only partially, right? Only evaluating for certain values of y1, right? So this is called a truncated moment. So your Lindeberg condition is basically trying to establish that the limit of this in the limit this truncated this is a truncated second moment, right? The truncated second moment is equal to 0. Okay. So and then of course if you write it, express it in terms of Lebesgue integral. So the Lebesgue integral will simply be this thing. I think by now you are familiar already, right? So this is the measure. Right? Okay, so this is the set, all right, where you apply the measure. Okay, and of course, if you are dealing with the usual commonly encountered family of distributions, then basically this Lebesgue integral will basically be just your Riemann integral, right? So you can use your usual Riemann integral to do the checking. Okay, so essentially you just need to show, so basically just show so you basically you can basically ignore this part because by assumption your variance must be larger than 0, right? So basically you should just concentrate on showing that this expectation, right, converges to 0, yeah, as n increases. Okay, so then don't get scared by this notation. Actually, it is actually quite easy to do. Okay, so we look at some examples, yeah. So this is your Lindeberg condition. Okay, so example. Suppose your x1, x2, and xn are exponential 1, right? Okay, exponential random variables with parameter 1. So this means your variance is 1 and your mu is 1, right? Okay, show that Sn minus 1 over, so this is mu, right? Over 1 over square root of n, which is, if you rearrange it, it can become something like this. Okay, this becomes like this, converges in distribution to standard normal, right? So basically you invoke, so your proof, you will invoke, you will check the Lindeberg condition. Okay, you check the Lindeberg condition. If it is if it holds, then if it's true, then you can invoke CLT. Right? Okay, so you just basically need to check this condition. So let's take a look. Now, so basically we want to evaluate this integral, right? So we have integral, okay? This one is x1 minus 1 more than equals to epsilon square root of n, right? Because your sigma is 1. And you have x1 minus 1. So you have a square there, right? Okay. And then you multiply it with the density of your exponential distribution. So you basically need to evaluate this integral, right? Let's say I call this I of n. Okay. All right. So as you can see here, so you can further write this as, okay, what is this? So basically what is this inequality? This inequality is basically, there are two parts, right? One part, it will be x1 greater than or equals to 1 plus epsilon square root of n. Okay, the other part will be x1 less than or equals to 1 minus epsilon over square root of n. Okay, so if you recall, the absolute of some random variable greater than alpha implies that x is greater than alpha or x is less than minus alpha, right? So you can basically use the same thing to obtain these two inequalities, right? And since they don't overlap, right, these two inequalities are mutually exclusive, okay? So they are disjoint. So basically, this integral over this disjoint set can be written as the sum of these two integrals, okay? All right. So now, basically, so once you have this notation, then basically you just need to tidy it up to what you are familiar with. So it's perfectly okay to write this, yeah? Okay. So then we write it in a more familiar form, which is okay. So come here. Come here. The integral 1 plus epsilon square root of n going towards infinity, right? Plus, so the upper bound is 1 minus this, so you have 1 minus epsilon square root of n. It goes until 0 only, yeah? Okay, and actually it is good to put the additional thing here. It is good to write something here. Indicator function x1 greater than 0. Indicator function x1 greater than 0. Okay. Because your at the lower level, you will basically write it just as this, okay? 0 elsewhere, all right? So now that you know indicator function, right, this is basically just equal to e of minus x times indicator function x greater than 0, right? Because when this condition is true, then it is 1, right? So you will get this term here. Otherwise, if it goes out of this, like for example, if x is negative and all that, so this will be 0, right? So, and then you will get this, okay? So for actually for theoretical work, it's better to write it like this rather than this. This is for undergrad, like first year level, right? Because they may not yet be mature enough to understand indicator functions, okay? But now you have studied indicator functions, so you should make use of them. So basically, you rearrange, you write it like this, okay? Now, once you have this form, right, you basically can consider the limit already. So how do you take the limit? What happens if you take limit? Let me clear some space here. Okay, so you take limit of in, right? Okay. So basically, what will happen to, so there are two terms here, right? What will happen to this first term when you take, when n tends to infinity? What will happen to this term? Of course, your epsilon is some arbitrary constant that's greater than 0, yeah? Okay. What will happen when n tends to infinity? Anybody? It's very obvious, yeah, what will happen when you take limit.
Is it 0, Doctor?
0. You're saying limit of this is equal to 0? It cannot be equal to 0, right? It can't be equal to 0 because over here you have at least 1, right? So yeah, I mean, you don't have to guess these things, isn't it? It's just a function of n, so you just need to look at it. Sutta says it's 1, but why is it 1? You got, okay, you have here, you got 1 plus, so the 1 is a constant, so you put limit on it, nothing happens. So you have this. What is this? Is it 1? Is it, Sutta, if you say this is 1, that means this limit is 0, you know. Is it clear? Is it obvious that it's 0? Your absolute is just some constant, right? That's greater than 0. Error is close to 0, epsilon, okay. Let's say you take your epsilon to be some very small value. Okay? Whatever, some very small value. But look at your n. Your n is tending to infinity, you know. Infinity can be something like this or whatever, you know. So even no matter how small you set your epsilon, you can set it to be extremely small. But eventually, because it's static, right? Because it's just a static, but your n can keep on increasing. So eventually your n is going to surpass your epsilon, isn't it? Right, in terms of the magnitude. So what will happen to this? What will it become? Yeah, it's infinity. It basically diverges. Why would you feel strange about the thing being divergent? It's very obvious from here. Your epsilon is a constant, and your n is, and it just depends on n. N just keeps on going, increasing until no n. So of course this thing will also diverge. All right. So there's nothing unusual. There's no trick involved here, right? It's just a direct thing. Okay. So it's infinity, yeah. So what will happen? So you know your lower limit of integration will tend to infinity. So what will happen here? So what will happen to this integral? If your lower limit of integration becomes infinity itself, you will get what?
Zero.
Yeah, that's right. You get 0 because when you take an integral and these two, the lower and upper limit is the same, you get 0, yeah, because that would be the integral at a single point, right? So that will give you 0. And what will happen to this term? If you take n to be very large, what will happen to 1 minus this?
Negative infinity.
Yeah, this is minus infinity, right? So you have minus infinity. Okay. So what will happen to this integral? So now you have from 0 to minus infinity. So you cannot claim that it's the same set to 0. But what can you say here? What is this integral? So focus on this part here. This thing is only non-zero when your x1 is greater than 0, right? So when you're integrating from 0, so from 0 to minus infinity, what is the function that you're integrating? Is it this function? What function? If your x is larger than 0, you are integrating this function, right? Okay. Now so if your x is now you're integrating from 0 to minus infinity. So what is the function in that interval? Is it still this function?
Is that 0?
Yeah. That function is actually 0 because you look at this indicator function here. When you're integrating from 0 to minus infinity, it's already out of this interval, you see. When you go out of this interval, this sets to 0. And this function here multiplied by 0 is 0. So basically, you are basically integrating. So you're basically integrating a 0 function, you know, over this interval. This is a flat line, right? You got a flat line here. And you go integrate from 0 to minus infinity. So of course, this is definitely 0, right? Okay. So basically, you get 0. Okay. So this is the result, right? When you evaluate the integral separately like this. Okay. So this is actually quite straightforward. If your calculus is not rusty, this is actually quite straightforward to do. Yeah. So so basically so for all these cases, right? Even if you replace it with, let's say, some other distribution. For example, you replace it with chi-square. You replace it with what else, like Laplace distribution, some other distributions, like for example log normal and whatever, right? It doesn't matter, whatever. What happens is that only this part, the functional form is different, but the argument is the same. They will integrate from certain intervals, and then the argument is very similar, right? That's why you have to use your indicator function here, because you will end up in a situation where this part here is a case of something like this, infinity over infinity. So this will take care easily. The other part will be something like this. And then you have to use the indicator function to argue that over this interval, the function is actually 0. So that integrates to 0 as well. Okay. So this is the Lindeberg condition, yeah? Okay. For this particular example. So later you try some other tutorials. You try tutorials, you will get practice on some other distributions, right? So this is the general idea. And now I move on to the Lyapunov condition. Okay. So the Lyapunov condition basically is the following. You just need to show that So this is a parameter delta, yeah. So your delta is larger than 0. Okay, and again, your y1 is the centered form. Mu is the expectation of x1, and sigma squared is the variance of x1. Okay. Now, in this form, right? Basically, you so let's say so basically you need you as long as you show that it holds for any particular value will do, right? You can, so you need to pick delta that works. Okay, so you just need to show that for actually this is for any. Yeah. Okay, so don't make your life difficult by choosing delta that is weird, like 0.12345. Okay, choose something that will make it easy. Okay, especially since over here you need to deal with the expectation of an absolute random variable, right? So how do you make, what are choices of delta that will make this expectation easy to evaluate? So over here, this one, unlike the previous case you're dealing with a truncated second moment, yeah? So this one, you're basically dealing with the 2 plus delta moment, yeah? And it's not truncated, right? But then you have to deal with the absolute, okay? 2 plus moment of the absolute of y1. Okay. So what choices of delta is natural that will make it easy? There's one candidate that comes to mind immediately. What is this value? Pick a value that will make this expectation easy to evaluate. Albert says 1. Any other opinions? Everybody agrees 1 is the easiest? Oh, Albert, you change your mind. You think 2 is better? One, two. Any other opinions? 2 as well. Sultan. Okay, so the easiest one is 2. You basically pick delta such that your 2 plus delta is even, right? Because when it's even, right, when you have absolute, you multiply with an even power. Basically then it disappears, right? It's the same as without the absolute. Then when you do your integral, it will be much easier. Because if you use an odd power, the problem is that when you have odd power, the problem is that if your x covers the entire real line, right? then power of 3, you will have to deal with negative value. So you keep have to consider the negative part and the positive part. So it's not that you can't do it, you can do it, but your working will be much more complicated. All right. So the easiest one is to pick your delta, and that definitely, since your delta is greater than 0, you have to work with something that's more than the second moment. All right. So the natural one is to pick delta equals to 2. Okay. So if you pick delta equals to 2, then for delta equals to 2, then the Lyapunov condition will becomes limit of this thing n sigma square n sigma square. So 2 divided by 2, so you get 1, right? Okay, and then over here your expectation of y1 power 2, okay, power 4. So this is the fourth moment of y1. Okay, now look at this part here. So basically this will be cancel, right? So you cancel this. So basically it's a limit of this. Okay. Now, what is it that you need to show here? You need to show that this is equal to 0, right? So when will this result be true? So what do you need to evaluate here in order to claim that this limit is equal to 0? What is needed? What needs to be checked? Expectation of y? Why check expectation of y?
Check the variance is larger than 0.
Yeah, of course. Yeah, of course. That one is definitely right. So these are already. So this is finite. Okay, this is also finite, right? Okay, fine. These are the standard conditions. I'm looking at here. So if you want to claim that limit of this thing is equal to 0, what should you check? Because obviously your denominator has an n, right? So your denominator will grow very large, right? But what is there to check here? For you to claim that this is equal to 0, what do you need to check? You can't just say that this is equal to 0. You need to check one thing. What is it?
y1 is finite.
Yeah. You have to check that the numerator here is finite. Must be finite, right? Because it's possible for your moment here to be infinite, you know. Yeah? If this is infinite and your denominator is going to infinity, so you have a case of infinity over infinity. So it's unclear what is going to happen, you know. Yeah? So you cannot just see this part, the denominator is n, straight away go to 0, yeah? Because it depends on your numerator here, this expectation being a finite number. If it's finite, then of course it will be obvious that it will be the limit is 0. But if it's not finite, then we don't know what is going to happen, right? So if it's not finite, then maybe this part depends on n as well. Then you will have to maybe use L'Hopital's rule or whatever, yeah? Okay. So then what needs to be checked is basically you check that the expectation of the fourth moment is finite. Okay, this is what you need to check for the Lyapunov condition, right? In spite the fact that it looks so scary here. At the end, it just boils down to checking, well, just need to check the fourth moment is finite, all right? Then it becomes a simple, just a simple problem in dealing with inequalities, okay? So now we are going to check this thing using the previous example of the exponential distribution, yeah? So now we establish if you choose delta equals to 2, then basically you just need to check this condition, right? And most of the time you just choose delta equals to 2. Okay, for most problems that will work, right? Okay, let's clear this. So, so I've got x, so just now x1, x2, and xn exponential 1. So my mu is 1, my variance is 1, okay? So I want to check the Lyapunov condition, right? So after stating, so basically I choose delta equals to 2. So this implies that I will just need to check that y1 power 4 is finite, right? Which means I need to check expectation of this is finite. Okay, your mu is 1, yeah? Which basically means I just need to check this integral. Is finite. Okay, so basically show that this is finite. Okay, how do I argue that this integral is finite? Now, of course, the simplest way is to basically just evaluate it, right? You basically evaluate it and you get some number and then you're done, right? So it's a number, so of course it's finite, right? But in this case, it is perhaps not so easy to evaluate this. Well, maybe it is, right? But it's a bit very tedious because well, after you probably have to make some change of variable like u equals to x1 minus 1, then make a replacement. So you know, then your du is dx1. So you make replacements like this, then you will change the interval integration, and you can then do this integral. Okay, let's see what happens if you try to do that. So you will get something like this. Your x1 will be u plus 1 du. So when your x1 is 0, your u will be minus 1. And go to infinity, right? Okay, so you can try to evaluate these, which is going to be very tedious because you have to apply the part-by-part integration multiple times, all right? It's very, you don't really want to do that, okay, if you can avoid it. So use a smarter method, right? You just need to show that it's finite. So what do? You just show that this integral is basically bounded. Yeah, if you can show that this integral is bounded, then you're done already, right? Because if it has an upper bound, then surely it is finite, right? So our strategy is to show that the integral is bounded. Okay. So to show that it's actually bounded, so you will have to consider some kind of analysis, right? Okay, let's look at this one. Now look at this. This is x1 minus 1, right? So let me write the integral. Let's say I write as I. Now look at this carefully. I can write it like this. Plus Then I have 2. Then I've got plus between 1 and 2. All right, agreed? So I got 3 parts from 0 to 1, 2 to infinity, and 1 to 2. Now, when your limit of integration is going from 0 to 1, you look at this thing. So your x is going between 0 and 1, right? When your x is between 0 and 1, then you subtract 1. So you're going to get a fraction, right? You're going to get some value that's between 0 and 1, okay? And you raise it to the power of 4, so this value will become smaller than 1, right? Okay? So basically, when you go like this, so the first part here, this will be bounded by x1 power 4 e minus x1 dx1. And in fact, this will be further bounded by 0, 1 e of minus x1 dx1. Okay, so I want you to see the chain of argument here. When you say, let me repeat. So from 0 to 1, your x1 minus 1 will be some, so x1 minus 1 will definitely be less than or equals to x1, right? Because you're taking this value and you're subtracting 1 from it, okay? So it will be some value between 0 to 1, right? Okay, so it'll be less than this one. And since so you can further bound it with 1 here, because your x1, right, is between 0 and 1. So raised to the power of 4, it will be definitely bounded by 1, right? So by doing so, you get a simple result here. So basically here, you basically have 1 minus e of minus 1, okay? So this is finite, okay? Then we settle at this part, okay? So this part here, now when it is from 2 and above, right? When it's from 2 and above, so this will be, we have something like 2, you subtract 1, it will be more than 1, right? So basically this will be bounded by x1 power of 4 e minus x1 dx1. Okay? Yeah? You can imagine if you sub in a 2 here, you will get 1. So it's definitely less than if you sub in a 2, so you get 2 power of 4 is larger than 1 power of 4. Okay. Right. So this is bounded by this term here. And so this is basically the definitely less than or equals to 0 until here, right? Okay, so this one is you're integrating from 2 to infinity. Definitely less than or equals to integrating from this to here. Okay, so basically this is the fourth moment of the exponential distribution, right? Okay, so this one is definitely finite because you can actually use the moment generating function to find out the fourth moment, yeah, of the exponential distribution. Okay, so it will be some value that is finite. Okay, you can use over here. So you reduce it to the moment of the distribution that you want to look at, all right, and then you can use moment generating function. So after that, so we established that this is finite. This is finite. So basically, you don't actually need to show the bound for everything. You don't need to show that this is less than or equals to some bound. After you split the problem into 3 parts, you just need to show that all these 3 parts are bounded, right? So again, you make a big problem into similar sub problems, and then you solve each of them, right? So the problem becomes easy. So you show that first part already show that it's bounded. Second part show that it's bounded. Now we just need to show this part is bounded. Okay. So again, this part here from between 1 and 2, right? So between 1 and 2, so this part here will still be a fraction, right? So again, so this will be less than or equals to x1 4 e minus x1 dx1, and therefore this will, okay, so be bounded by this term here. Okay, and this term is definitely bounded. So you don't have to show that this is bounded anymore, because if you manage to show that this is bounded, right, then this there is definitely bounded, because this is running from 1 to 2, whereas this one is running from 0 to infinity. Okay, so basically once you successfully show this, so the only kind of like a bit hard work is to show the moment generating function moment here, and once you have shown this, this is basically trivial. Okay, because it's this one is nested inside here. All right, so this is the strategy to show to check Lyapunov's condition. All right, so you have to have some ability to work with inequalities. Yeah, that's why we previously have quite a bit of examples on how to deal with inequalities. Right, so you'll find that inequalities are very useful in this kind of setting. Okay, so you have to switch on to some kind of mode of thinking, which is bounding. Yeah. All right, finding bounds. Okay, so that will be all that I want to talk about for central limit theorem. Here, basically, today we just look at the statement of the central limit theorem, and also the two conditions, right? One is the Lindeberg condition, and one is the Lyapunov condition. Okay, either one of these conditions, if it holds, then it implies the CLT. Okay, so you can use either one of them to check. Okay, so let's take a 10-minute break now, and when we come back, so please the students who are assigned to do tutorial 5, please get ready. Yeah.
Can you see my screen here?
Okay.
So basically, question asks us to find the expectation for the absolute value of x. So what I did is I used this summation, then I sub in all the value inside, and this 1/4 is just by subtracting 1/4 minus 0. This 1/2, I get this 3/4 minus 1/4 as the Lebesgue measure, and also for this 1/4, I get by subtracting 1 from 3/4. So end up I getting, because this is absolute value of x, right? So I modulus it, so it positive value. So end up I getting the expectation of absolute value of x is 7/4. For number 2, I have to show that the absolute value for expectation of x is smaller or equal to expectation of absolute value of x. So what I do, I calculate the absolute value of expectation of x first, and I got 3/4, and I conclude that it is less or equals to expectation of absolute value of x, which is equals to 7/4. But I don't know whether this is what the question asks. So I actually generate also, like by using the triangle inequality. And finally, I got this as my conclusion.
Triangle inequality. Okay. expectation of or how do you do the triangle inequality? Okay, never mind. Let me go back to the previous one, number 2. Part 2. How did you get 3/4?
Just simple addition.
To
I did it wrongly.
oh, okay, right, okay. Okay, thanks, Eugene. So I just give some explanation here. The first two are actually okay, but I just show you a little bit on how to visualize it, right? So you have x of this is -2, 0, 1/4, 1/4 to 3/4, 3/4 to 1. Okay. So basically, if you sketch it, this is your x. So you will have from so -2 is -2 is here. So from 0 until 1/4, you have this line, right? And then from 1/4 to 3/4, you have 1. So from here, you have 3/4, right? And then from 3/4 to, oh, sorry, it doesn't have, it should be empty. Okay. And then from 3/4 to 1, you have, so -3 is here, so you have here. Okay. It's 1. Okay, so you want to find expectation of absolute of x. So by definition, right? Okay, by definition, you have this, yeah? Okay, so once you take absolute of x, so basically you have, so this is x, right? So the absolute of x will be like this one will flip up, right? So you can do the flipping yourself, okay? Okay, you do the flipping yourself. So basically it will be, like for example here, there will be 2 times the measure, the Lindeberg measure on the length. Then add, this is 1 times the Lindeberg measure on this interval, which is 1/2, and plus the Lindeberg measure on this interval for 3, yeah? That's 1/4. So this will be 4 out of 7, right? Okay, this is as I mean, I just want to show it graphically, right? Okay, so that it is clear. Of course, if you do it analytically, it is also correct. Now, how about the expectation of x? Now, if you use Lindeberg integral to, when you are asked to do expectation of x, right, by Lindeberg integral, so it will go by this, right? And this one by Lindeberg integral, this is equal to the positive part. Subtract the negative part, right? Okay, so what's the positive part? The positive part will be just this line, right? The positive part is basically just this line, okay? And the negative part is this one will flip up, so we'll go to 2, and then it's 0, okay, and then after that it has 3, right? 3 from here. It's 2, this 3. Now over here it is actually flat, okay. This is so flat, right? Okay. So clearly the Lindeberg measure for x plus here is basically, so this part is 0, 0, so you don't have to care about that. So there will be just that interval. So this is 1, right? So 1 times 1 over 2 minus, so this part, right? So this part is you sum both of them, so you will get 2 times 1 over 4 plus 3 times 1 over 4, okay? So this will be 2 over 4 minus 5 over 4, so you get minus 3 over 4. Sorry, minus 3 over 4. Right. Okay, is that what you got, Yuji?
Yes.
Yeah. Okay.
Negative 3. Yeah.
Huh? Sorry.
Yeah, I got but I got the modulus value for absolute value for negative 3 over 4 instead of negative 3 over 4. Instead of I modulus it.
Oh no, there is no modulus because you're asking for expectation of x. Sorry, it's asking for expectation. Oh, it's asking for what? What's the question again? Expectation of x, right?
Absolute value for expectation of x, isn't it?
Oh, asking for this, right?
Yes.
Okay, so you take absolute of it. Yeah, so since you find this, then you take absolute is 3 over 4, okay? And then they ask the last one is verify that expectation of x less than or equals to this. I mean, like this is asking you to verify only, so you just basically need to check. It's not asking you to prove. So verify basically means that you just check lah. So here this one is 3 over 4. This one expectation of absolute x is 7 over 4, right? So this is definitely less than, right? Okay. If you want to prove it, it's actually this is actually the proof is very simple. You just need to invoke Jensen's inequality because this is a absolute function, right? The absolute function of x is convex. So you can apply Jensen's inequality and you will straight away get this inequality, right? But here, in this case, at that time I haven't taught Jensen's inequality yet, so so that's why I just say you verify, yeah. Okay, but this is true in general by Jensen's inequality. Okay. Right. Okay. Is that okay? For using Lindeberg integration to calculate expectations. All right, okay, so let's go to question 3. So Qiu Jiasheng will present.
Hello?
Yeah.
Can everyone see my screen?
Yes.
Okay. So for my question 3, I need to show that the fx when integrate from 0 to 2 is equal to 1. So we know that this function is a well-behaved function. So we can use the Riemann integral instead of the Lindeberg integral. So we will basically just integrate basic, then we will get 1. Then for part 2, because A is infinitely large but countable set over 0 to 2, so we will let A is 0 to 2 intersect with a rational number. Then when the probability of A is equal to integrate AF d mu, then this one we will use the Lindeberg measure, because we know the Lindeberg measure of this set A is 0 because A is countable set. So 0 times the infimum of fx is equal to 0. So probability of A is equal to 0. Okay, then part 3. Part 3, to be honest, I like do part 4 first, then do part 3. Yeah. Then for my part 3, how to find the expectation using the Lindeberg integration is basically we will just write this one. No? Then because we know the indicator function is equal to this one, then we'll sub inside. Then this one we can interchange by Fubini theorem. Then this one basically is the expectation of the indicator function. Then we will get this one. And when x is greater than x is true, so is left with this one, and this one is 0. So we will get this one. Then for this one, because I tested out like xfx is equal to 3/2. So I was thinking to make this one by when doing the part 4 is equal to 3/2. So I let w is equal to when x is equal to 0.5 is from 0 to 1 with no the rational number from 0 to 1. And when 1 is 1 to 2 with the rational number not minus the rational number inside 1 to 2. Then at 1.5 is 0 to 2 intersect with the rational number. Then in part 4, we want to find the expectation. So the expectation, we will find the Lindeberg measure of this one is equal to, this one is equal to 1. And for this one also equal to 1. And this one we know because it's equal to 0 because it's countable. Then, so we will use basically just 0.5 times 1 plus 1 plus 1.5 times 0 is 1.5. Then for this pattern one, we want to find the tail probability. So we will integrate from x to 2 because the thing is from 0 to 2. Then we will sub inside the function and we will get this one is the tail probability function. Then we will substitute inside, then do basic integration. Then we will get 1.5. So it's equal. So.
Okay. First thing I have to apologize because actually I left out one. If you look at this, it cannot be. I mean, by definition, there's an x. It's actually left out.
Oh, it is x and fx.
It's actually an x here. So
but at here I have do this because this one I think is p x greater than equal to
it doesn't equal to this thing. It cannot be equal to this thing because your integral of is go by definition, right? So there should be an x there. Okay, so I left out the x somehow, and I just noticed it.
Okay.
So okay, then there's some kind of discrepancy there. Okay, thank you for your presentation.
Thank you. What should I click now?
You just stop sharing.
Okay.
Okay, I just go through this a bit. So, okay, so the 3A, the solution is correct. So you basically that Lindeberg integral is just the same as the Riemann integral. So you just use Riemann integral to evaluate. So you will get 1, right? Then for the second part, let's say the construction, you can use the rational numbers, right? You can use like 0 to intersect with Q, right? That's fine. Here I just use this construction. Basically, I start from 2, I halve it, I halve it, I halve it, and so on. I just keep halving it, right? So I construct it like this, and therefore P of A is integral. So the Lindeberg measure, right, is equal to 0 because yeah, like your argument, because your A is countable, right? And Lebesgue measure of a countable set is 0. Okay. All right. So definitely so this is a Lebesgue measure. So this is definitely 0. Okay. So this is settled. Then the third part is asking about how to explain finding this, right? Using the, I mean, like, so this part is more like trying to see whether you understand how to apply Lebesgue integration, right? So basically this is x omega dp, right? So this omega is your 0, 2, okay? Now by so basically this is a Lebesgue integral, right? This is a Lebesgue integral, which basically is also something about you know your definition of Lebesgue integral, right? It's it will be the infimum of so this will be your x omega, okay? So basically you have the graph like this. This is your x, okay? Right? So you apply a measure on. I use a 0.5, then I have 1, then I have 1.5, right? So I got so I got this this interval here. Okay. So we cut if you cut here. So remember your Lebesgue is cutting on the y, it's not cutting from the x. You cut here, you get, so you cut one here, then you cut the other one here, and then you cut another one, because this is your x, this is your line here, yeah, x, this is a 45-degree line, right? So when you cut like this, then you make a projection downwards. So you basically will get these 3 rectangles, right? So this is cutting at 0.5, cutting at 1, cutting at 1.5, okay? So your infimum of these, for this equals, so you, let's say I have the set, so basically there's another set here, right? So this is your A1, it's your A2, it's your A3, this is your A4, right? So infimum of this AI, right? So there will be, so across this set, so the over here for this set, the infimum is 0. For this set, the infimum is 0.5. For this set here, the infimum is 1, and so on, right? Then multiply by the measure, right? The measure of AI, right? Where this measure is actually an integral, okay? So it's not the Lebesgue integral on this line, but it's the measure of A here is defined as this guy here, the area under the curve, okay? So you have to be a bit careful here. So the measure here, so again, the Lebesgue measure is like you have the infimum multiplied by the measure of the set, right? So therefore you get the area under the curve, okay? And then you try to sum them, right? Okay, you try to sum them, and then you take the supremum. All right, so this will be your integral of x is actually equal to this. Now, in this case where you only have these 3 partitions, because this is a soup, right? You maximize it. So, but if you only have these 3 groups, these 3 partitions, your sum here will be 0.5 times p of the first one is 0 times p of A1 plus 0.5 times p of A2 plus 1 times p of A3 and plus 1.5 times p of A4. So your P1, PA1, A2, A3, A4 is found by this Lebesgue integral, yeah, okay. F d mu, right? So this will basically be, for example, A1 will be from 0 to 0.5, okay, of 3x squared over 8 dx, all right, some value, and so on and so forth, right? So, but then the first one you can basically ignore because multiplying by 0, okay? So you just need to compute this 3, and then you can find some value, okay? It won't be the exact one, but it's just an approximation, okay? The whole thing is that you have to argue like this, right? To show that you understand how the Lebesgue integral is actually done through measuring the sizes of these rectangles, okay? I think the main difference here is that this measure, this is a measure on the set A1, and this measure is computed as this Lebesgue integral, okay? So after that, basically then your expectation of x is basically just when you find the soup, right? When you find the soup, so basically it's just then you revert to your Riemann integral, right? And then you just evaluate. Okay, you will find that this value here is this value here is actually approximately equal to this value. Okay. So later you can check the solution, yeah, for more details. Okay, so let's move on to question 4. Question 4 also there's a small typo, left out one number there. So maybe you will be able to find it. Okay, let's go to question 4, Parvin. Parvin?
Yeah, doctor. Can you hear me?
Yeah, okay.
Okay, for question 4, x is a standard normal random variable. So our mean is 0 and variance is 1. So applying Markov's inequality for alpha greater than 0, we find the expectation of x. So by using the PDF of standard normal random variable. So here, since x is non-negative for Markov inequalities, we take from 0 until infinity. And here, for any alpha greater than 0, we change the interval from alpha to infinity. And since the x is greater than alpha in integrated region, we replace x with alpha here. So when you factorize out the alpha here, we can write in terms of probability x greater than alpha. So when I rewrite it, I get probability of x greater than alpha less than equals to expectation of x over alpha. So my expectation of x is I find through here. So the value I get is 1 over SIT2 pi. So when I substitute back here, I get 1 over alpha SIT2 pi as shown in the question. Am I correct until now, doctor?
You just need to start with I think you just need to start with okay, let me see. I can annotate the screen. You just need to start here. I think there are some this part there might be something that is not watertight. So you start here by this one is by Markov. Well, your Markov inequality, right? You're starting with you see you cannot start with this because this one is for this result is basically for positive x, whereas your x, right, can go to negative, right?
Yes, doctor.
So you have to use this. You have to use this form.
Okay.
Okay. So you use this form, right?
Okay.
Start from here. Now, okay. So you found this expectation of well, then you need to find the expectation of absolute of x. So basically,
okay.
this is you take absolute of x times this is the fx, this is the normal density, right?
Yes.
So basically you have one part, okay. Now this is an basically this is actually twice of this because this is an even function.
Yeah, symmetry.
So this is an even function. So because when you put x like even functions, right? So even function. So let's say this is your gx.
Okay.
So even functions means g minus x is equal to gx, right? You can check, right? G of minus x is basically minus x absolute f of minus x, right? So this is x. This is basically x because your normal density, right, is 1 over square root 2 pi e of minus x squared over 2. You change this to minus x, it's still the same, right? Okay. So this is basically an even function. When you take an integral from minus infinity to infinity for even function, then you can basically start from 0 to infinity, take half of it, and then multiply by 2, right? So that's why over here, so you have done this part here. So you got 1 over square root of 2 pi, but it's only half, so you're going to multiply by 2. So this will be twice of 1 over square root of 2 pi, which is square root of 2 over pi. Okay, so you got this. Now this part here is equal to x larger than alpha plus px less than minus alpha, right? Because it's two-sided.
Yeah.
Yeah. So, but then it's by symmetry, right? Yeah. This one is normal, so this is symmetric, right? So this can be written as 2px greater than alpha. This only works for symmetric distributions, yeah. By the way. So then you have the left-hand side is equal to 2 of this bounded by square root of 2 over pi divided by alpha, right? So therefore, your p of x greater than alpha is bounded by, so you take the 2 goes down there, so you get your 1 over alpha square root of 2 pi. Okay. So there are some parts of your argument that got some holes there. Okay, so you can review this later, yeah?
Okay. All right, doctor. So for the next part, to apply the Chebyshev inequalities. So this is the inequality for Chebyshev. So our mean is 0 for single normal random variable, and then so here I get probability of x greater than alpha, and here this will become variance of x. So the variance of standard normal random variable is 1. So that's why I get 1 over alpha squared.
Yeah, okay, sorry. So this part here, actually, I made a mistake. I forgot to type the 2 here. There should be a 2 here. Because if you use Chebyshev here, this is basically absolute, isn't it?
Yeah.
You can't just, because this is a norm, this normal is going by positive side and negative side, right? Negative side and positive side. So you cannot simply just drop the absolute, right? So up to this point is okay. So this is basically just 1. But again here, so you will have twice of p x greater than alpha bounded by this. So basically there should be a 2 there.
All right.
Okay, so yeah, so there's a bit of a hole in the argument there, yeah.
Okay.
Okay, there should be a 2, but I didn't spot the thing until now, just now. Okay.
So I think the next one also, the Cantor-Lewis inequality also, I think should be a 2 also, right? Because it's absolute. Oh no. I think no.
Yeah, okay. The Cantelli, okay, Cantelli inequality, right? There is actually a two-sided version. The two-sided version is like this. There's a two, I think I didn't talk about, I left out this part. Supposed to put it in notes, but never mind, it's okay. So two-sided, this is the two-sided Cantelli. So you will get this thing. Then you will get 2 over 1 plus alpha square, right? So again, this will be twice of this. So you will end up canceling this, okay?
Yeah.
Okay, it's okay. This basically is just applying the Cantelli inequality for two-sided case.
Okay. So I think for the last one, to find integral alpha, I'm not sure this is the correct method, but I think the values are different now. So it
Well, it's okay as long as you are using the so I think this one is okay. This one, because these two are okay. This one has a 2 here. So this one basically you are basically you are basically just solving for
alpha.
right. So basically this one, your quadratic equation is +1 less than 0, right?
Yeah.
So basically you are so your curve is basically 0, 0. Let me see. So this should be when your alpha is 0, so you end up at 1. So it's some situation like this, I think. Okay. So you're basically trying to find these two roots, right? Because at this interval, you basically have a negative, isn't it?
Yeah.
Correct?
Yeah.
This quadratic curve has a minimum, right? That goes like this, right?
Yeah.
So these are the two roots. So basically you are trying to find I think here you're finding a root, right? You're finding a root here.
Yeah, correct.
2 pi plus minus square root of 2 pi minus 4 divided by 2. Okay. So basically you're finding these 2 points, and then yeah. So your alpha is running between these two values. Okay.
Okay.
In this interval, your Markov inequality your Markov bound will be sharper than the Cantelli bound. So then, of course, for here you have another situation, right? So basically, you just need to adjust, right? Just adjust a bit, okay.
Okay.
So the reason for this question is to show you that actually these bounds are sometimes certain bound is better than the other bound for estimation, depending on what is your alpha. Okay, so it's not to say that one of the bound will always win all the time. Yeah, it depends on what is your alpha. Okay.
Okay.
Thanks, Pavan.
All right. Thank you, Doctor.
Okay, so we're running a bit late, so sorry about that. Just go to the last question. Atira, is it?
Yes, Doctor.
Okay.
Can you see my screen?
Yeah.
Okay, for the question 5, we need to find the EX using the sum of tail probabilities formula for non-negative discrete random variable, and then verify the answer using the standard definition. So first of all, geometric distribution given is P x equal to x equal to 1 minus theta to the power of x minus 1 theta, where the x trials are equal to 1, 2, and c. Therefore, I change it to q and p, so I get q to the power of x minus 1p because p plus p is 1. And then find the CDF for p x less than equal to k equal to 1 minus p x greater than k. So p x greater than k equal to p x greater equal to k plus 1 equal to sum of x equal to k plus 1 until infinity 1 minus p to the power of x minus 1 p. And then I get 1 minus p to the power of k, which is q to the power of k. And then for the tail sum formula, ex, sum of we use the sum because this is a discrete random variable like the mean. Then sum of k equal to 1 until infinity px greater equal than k. 1 plus q squared plus etc. And then got 1 over 1 minus q and 1 minus p. For the verification, standard definition, ex equal to x equal to 1, sum of until infinity. So px 1 minus p to the power of x minus 1 get p over 1 minus p to the power of 2 equal to p over p squared equal to 1 over p, and then verify.
Okay, can you scroll up a bit? So why do you use this result? Because scroll down. Because you are asked for, you need to use this. So how to connect? I know at the end you get the correct answer, but I'm just trying to.
This one, doctor, actually I'm not very sure because this one is equal to k plus 1.
Yeah, so you
then,
set, if you basically set this to be equal to x, then basically you just need to check like this, isn't it? 1 minus theta power of x minus 1 theta, right?
Yes.
Right. So basically then, sorry, this is k. So then basically you will get then you make a change already, isn't it? You change this to p.
Yes.
Okay, you don't actually need to change it because after changing it's still the same. So you just keep it, and here you can write out your things like this, right? So you have your theta, 1 minus theta x minus 1 plus 1 minus theta power of x plus 1 minus theta x plus 1 and so on, right? And then you can factorize, so you have theta 1 minus theta x minus 1. So then the rest will be 1 plus 1 minus theta plus 1 minus theta squared and so on, right?
Yes.
So then that will be a geometric sum, which is 1 over 1 minus theta, right?
Yes.
It's a common factor. So this geometric sum, so this will be 1 over theta, so this will cancel this. So you are ending up with this guy here. Okay?
Okay.
So then basically you just put in this guy, so this will be 1 minus theta power of x minus 1.
But doctor, for the tail sum formula, is it like we follow the k is equal to 1 because I saw the formula equal to 0.
I mean, this one you can write it as, I mean, like it's just indexing. So here you can write as x, no problem, small x.
But the starting is 1 followed by from the question.
Yeah, it's starting from 1. This is correct.
Okay, doctor.
It's correct here. So your general case is x, right? So you already found it from here is 1 minus theta x power of minus 1. So you just sub in this thing, right? So basically you're evaluating this sum. And this sum, if you sum in everything, so the first term is 1, second term is 1 minus theta, third term is 1 minus theta squared. Again, it is a geometric series, right?
Yes.
So that's why it will be 1 over 1 minus theta, so it will be 1 over theta.
Okay, so just need to change this.
Yeah, you don't have to because you are introducing unnecessary notation.
Okay.
Okay, so you get 1 over theta, that's fine. Okay, then you go below. So I want to ask you how you can go straight from here to here.
This one is the calculation like from the general geometric distribution of mean.
Can you?
Do I need to like show the calculation?
Actually, I'm just wondering how clear is it that the sum of P, sorry, the sum of so x1 minus p x minus 1. So you have this, right? I'm just wondering how clear is it to you that this series is equal to this?
Oh, this one, the formula like AKR. I use like the AKR equal to A over 1 minus R to the power of 2.
Can you show it? I mean, I know here you are referring to some formula and then you just plug in, right?
Oh yes. Like the P is A, the X is K, and 1 minus P.
Yeah, sure. It's just the indexing. Okay. My question is, do you know why this sum is equal to this?
No.
I mean, like plug in is very simple, right? You just you find some reference for a formula, you just plug in. Okay, fine, that's fine. If you don't have that reference to the formula, you come to this point. Can you work out this result?
No.
Okay, so this will be actually harder to do, right? If you don't have a reference for this formula, it will be harder for you to come to here, isn't it?
So I must show the calculation. Supposedly.
Yeah, because you have to explain why you suddenly come from here to here. Okay. So anyway, the point is that if you use this result here, you basically are just applying your geometric series 2 times, right? Whereas if you use the definition, you will come across the need to evaluate this sum, and if you know your calculus from first principle, then you may be able to get this. But I just want to check whether you know that.
Okay, I will try to do the more detailed calculation to get the 1 over P. Not just use the formula of index.
Because this one, you will need to, let me clear this. So for this, you will have to, in order to show this result, okay, so you have to do the following. So now I know that, first I know that this thing, okay, so this is a geometric series, right? Okay, this geometric series, and I know that this is 1 over 1 minus this, okay? All right, agree?
Yes.
Okay. If I take, so then I take derivative on both sides. So what will happen? So on the left side, the derivative can move inside the sum. So you will get you get x minus, right? So your x now will start, instead of 0, start from 1, right? Because this is the same as taking derivative of this thing, right? So you're basically starting from 1 already, not from 0. So then over here you get minus 1 over theta square, right? Okay, so the minus will cancel. Okay, so this is how you get your formula here. This is where the square actually comes out, right? Yeah.
Yeah.
Okay, so you have to you go back and check again using this method, right? You have to start with the geometric series. Start with geometric series representation, right? And then you take the derivative on both sides. Then you can get this result.
Okay.
Okay. So my point is that if you know the calculus properly, then you don't have to memorize this formula and you don't have to refer, because they basically are just a consequence of starting from the basic result and then taking applying standard calculus operation. Okay, you just check back on this, yeah? Okay.
Thank you.
Thank you. Right, okay, so that's all for the tutorial. Sorry, I used up extra time. Okay, but have to finish that, right? Okay, thank you everyone. So I'm going to end the meeting now.